All right, so now we're going to talk about Newell and Simon and the search space model. So Newell and Simon viewed intelligence as general problem-solving ability. And they argued sort of that is what makes humans intelligent, is our ability to solve problems more generally, right? So if you think of other kinds of animals, a lot of other animals have evolved specific abilities to solve very specific problems. I can't think of any off the top of my head, but you can find them all throughout nature where, different species have come up with solutions to an environmental problem, a problem of getting food or maybe mating with some other member of that species. So, but the thing is that most of those animals they solve very specific problems. So natural selection has led to them solving a very, very specific problem. The idea is that what makes humans so intelligent is that we can solve things more generally. This is true also with machines, right? Most machines are single purpose. They only have one purpose. So, for example, a refrigerator solves the problem of getting of food getting warm. A coffee maker makes coffee. A washing machine makes clothes. And so, yeah, these are all machines that are designed to solve one very specific problem. And similarly, it's not difficult to write a program that plays tic-tac-toe or checkers, but these problems would only work on a very specific problem of winning one specific game. And most AI pre-2020 was like this. And in such cases, you would have to tell the program what kind of problem it'll work on, what the conditions of success look like, and what operations are available to it before it could try and solve it. However, the kinds of problems that humans can solve, are much less specialized. We're able to deal with a variety of different problems from a number of different domains. So, in other words, we are general problem solvers. And so, with that in mind, Newell and Simon wanted to mechanize problem solving in such a way that would allow them to build some sort of general problem solver program. And hence, the idea was that if they did this, genuine artificial intelligence would have been achieved. Uh, yeah, so the idea was that if you could build a machine that was a general problem solver, then in a sense, you've built a machine that was genuinely intelligent according to their definition. Of course, spoiler alert, this program didn't work in its most ambitious sense. However, as with most productive scientific endeavors, its or semi-failure provided many insights about how the mind probably works, which is that's the gold standard for science in my book. And so they built they actually did this. They built a program, and this program could prove a number of theorems in logic as well as a number of other problems, right? So they focused on things like logic and math. And the idea was that such problems represented the kinds of problems that were suited for human level intelligence. They were quintessentially human level intelligent type problems. And in retrospect, it seems like this was one of their original sins, right? To focus on problems that were quite well defined and well suited for a program to solve. For example, computers are really good at following a set of well-defined rules that lead you to the correct answer. And so chess was assumed to be the ideal program. They thought if they could simply solve chess, right, have a program beat humans on in chess, this would be like the gold standard, and we probably would have, genuine intelligent. We could say that the program is genuinely intelligent. But computers are really good at that. They're really good at chess because chess has well-defined rules. And so those well-defined rules, you just tell a computer those well-defined rules, and it'll figure in, with some programming chops, you can get a program to play chess pretty well. However, the problem is that computers have much more difficulty with the kinds of problems that we're really good at. And so many of the things that we can do as humans, like perceptual problems, they're really easy for us, but they're really difficult for computers. And so this is why reCAPTCHA works. And the idea is maybe it would have been better if the search space model of Newell and Simon hadn't focused so much on well-defined games or well-defined problems. And so, yeah, one of the errors that they made was in assuming that logic and math problems, as well as chess, were quintessentially human-like problems and not other kinds of problems in which there is no definitive solution, or for ill-defined problems, which we'll talk about. Um, and so they argued that most, if not all, problem solving can be broken down into a number of parts, right? So they essentially said that problem solving is searching through a space of states, right? Of potential solutions until you find the correct solution. Um, so there's like an initial state, that's where you start. There's a goal state, which is how you want, the goal of what you want to do and of how, a problem would be solved. If you reach that goal state, then the problem would be solved. And then there were operators, so rules for how to transform from one state to another. And then there was the problem solution or the search space or the solution space. I'll use those interchangeably. And this is the path that was taken to get to a goal state. And they state that solving a problem is simply about using the operators or the rules of transformation to get from your initial state to your goal state. So, for example, if my initial state is hunger and my goal state is to not be hungry, then I would use a set of actions to get from my initial state of hunger to my goal state of not being hungry. In the context of chess, my initial state is the initial configuration of chess pieces, and I use the rules of the game to try and get to the goal state of putting my opponent's king in checkmate. And so, yeah, the interesting thing is that they argue that problem solving is simply about searching through a solution space by applying the operators in order to find the goal state, and that you would simply follow the path that leads to the correct solution. So they said, a problem first needs to be specified. And to specify it, you need a description of the objects, the rules or operators, and the goal state. So, for example, in chess, the chess pieces are objects, the rules for how to play the game, those are the operators. And the goal is to put your opponent in checkmate. And if you do this, there's this search space, right, or solution space. It's sort of a branching tree or a decision tree of achieved states defined by applying rules or operators to the initial state. So if my initial state in chess is like, how the chess pieces are arranged on a chessboard, right? Well, one path that I could take is moving one of my pawns. And another path that I can take, or the first move that I can take of a given path, is to move a different pawn, so on and so forth. And you already, right? There are about many different ways in which you can do your first move. And so, but even within the first move, there are many different other ways in which you can play the game, right? So if you moved the leftmost pawn up one, then your second move can be, well, all the possible moves that are available to you at that point. Okay, so in the next video, we're going to talk about problems with the search space model. But first, we'll talk a little bit about the traveling salesman problem.